Hello, everybody. My name is Ricardo Rocha. I'm presenting lab number 5, which is Choose Your Own Adventure. The name of my project is Falling from a Roof. I took this idea because in my city it is raining a lot nowadays. So I could see water falling from my roof and eventually to the ground. Something like this. As we can see here, water is falling over an inclined surface, then is following a parabolic motion down to the ground. So in this project, instead of using water, I decided to use an object which is going to slide over an inclined surface and eventually fall to the ground. I will use Tracker to analyze the data of a falling object. Then I will make a computer model using Python of the observed phenomenon. Then I will compare the analyzed real data with the computer model, and I will try to draw some conclusions. So instead of using water, as I told you before, I'm going to use an object. As you can see here, I will use a wooden object sliding over a wooden surface. It will fall over the inclined surface and will follow a parabolic motion. The height in this case is 1.4 meters. This is what happens. The object is falling down the surface, then is following a parabolic motion. As we can see here on the x-axis, at the beginning we have an accelerated motion until the time is approximately 0.434 seconds. After that time, we can see that the velocity on the x-axis won't change because from that moment the object is following a parabolic motion. On the y-axis, we have accelerated motion in both parts. Here we have an accelerated motion, but it's smaller than the one in the parabolic motion where we have an acceleration of 9.8 meters per second square pointing downwards. So we have an accelerated motion with small acceleration, then we have a bigger acceleration. So from Tracker, I obtained very important information, which is that at this time of 0.434 seconds, the object is leaving the surface and the whole motion ends at a time of 0.868 seconds. So with this information on Tracker, I made the simulation on Python. Basically, I imported all the information from Tracker into a CSV document, which I called Lab5 data.csv, and using Python, I could run the following model. So here we have the simulation. At the beginning, the object is following a straight line, inclined motion, then is following a parabolic motion. All this motion is obtained from Tracker. Then I will explain the physics that I made in order to perform the model. Well, when we have the inclined surface, the forces acting on the object are basically the normal force, the weight, and the kinetic friction. We have an angle of approximately 48 degrees. So here I inclined my reference frame in order to simplify the calculations. So using this reference frame, the sum of forces on the y-axis is 0, and I use this to find the normal force. Then the sum of forces on the x-axis is going to be equal to mass times acceleration using Newton's second law. This is the equation that I get. And using a coefficient of kinetic friction of 0.4, which is an acceptable coefficient for wood over wood motion, we get an acceleration of 4.92 meters per second square. Then using this angle of 48 degrees, I defined my directional vector for the acceleration, which as you can see is both negative on the x and y axis. Then on the parabolic motion part, the only force acting on the object is the weight, which is only 9.8 meters per second square, pointing downwards. So with all this information, I went to make my model, where first I defined the mass of the object, which is about 20 grams. I defined my acceleration due to gravity. I define my a hat vector, which is the directional vector for the acceleration, as we can see here. the j hat vector, which I will use for the weight, then the coefficient of kinetic friction, which is 0.4. Then I made my loop. As you can see here, I will use this time of 0.434 seconds, which corresponds to the inclined surface part. Then here I defined the weight acting on the object. I defined the friction acting on the object. Then the net force, which is the sum of both forces. Then I use Newton's second law to update the velocity and the position of the object. Here I put the corresponding code to draw the arrows. Then for the second part of the motion, for the parabolic motion, I use the final position and velocity of the first part of the motion, which are this, in order to make only the parabolic motion part. In this case, I use the last time, which is 0.868 seconds, to make the total motion. So here the only force acting on the object is the weight. So I define another net force, and I updated the velocity and the position for the object. Then when I run the model, this is what I get. As we can see here, the red arrow shows the friction force. The yellow arrow shows the component of the weight on the x-axis, in this case, or when the reference system is inclined, or corresponds to the direction of the acceleration in general. Then we have the parabolic motion part, where the only force acting on the object is the weight. As we can see, the motion is very similar to the one observed in the video. Then the final part of my project was to put both models together. So basically I joined the two codes where I imported the data from Tracker and I put them together. So this is what I get. We will see the red ball here at the beginning. Both are very close to each other over the inclined surface. Then we have a little separation, and we can see on the blue line the ideal trajectory, and on the red line we have the real trajectory. Here I have some trouble to match both of the motions. I had some trouble to match the timing between those two. I'm not very good at coding, so well, I did my best in this case. But as we can see here, at least at the beginning of the motion is very similar to each other. Then eventually in the parabolic motion, both are following a parabolic motion. So all the laws are being fulfilled here. So, well, I try my best in this final project. I use all the information that I got in this course, especially in coding. I'm not very good at coding, as I told you before. I try my best at this. I need to mention that I didn't consider drag force here because the object was very small and the motion was very short and there was no wind during the experiment. So, well, I hope you like this project. It was a pleasure. So I hope you like it. Goodbye.